Okay, so I was just listing the candidates today. So the third one is Najari Ali, who is remotely connected. Then Sabatucci, okay, Salustri, fine, and Sensolini Arra, fine. So we will follow this alphabetical order. You have been advised that you have 15 minutes plus discussion. So please keep on time and give time for discussion of your work. So the first presentation is by Imam. Let me look carefully. So he has done a thesis supervised by Professor Grisetti. The title is Line Segment-Based Islam. Please.
Test. Where's the QD? How's the full screen? I forgot.
Yeah, but you have also to shut the screen, otherwise your colleagues will not see you. Okay. Right, works, and then yeah.
Excellent. Thank you. Good morning, everyone. Good morning, everybody. My name is Ahmad Imam. Today I'll be presenting a 2D line-based 2D line segment-based SLAM, so supervised by Professor Giorgio Grisetti. Basically, in the world of autonomous mobile robotics, they basically utilize complex tasks. In order to do that efficiently, a map of the surroundings of the mobile robot is needed. However, usually the map that is provided is not accurate, and sometimes the robot is not equipped with a sensor that allows it to localize itself efficiently, such as GPS. Hence, research has allowed hence there is new research of simultaneous localization and mapping, which allows the robot using proprioceptive and exoceptive sensors to allow itself to both localize itself and adapt itself to its surroundings while creating an efficient enough map. In our project today, we will be presenting a SLAM concept that's based on line segments, that based on a line extraction algorithm that takes points coming in from the laser scanner, implement a feature-based extraction algorithm, in order to provide the line segment lines parameterized by its radius, its angles, and the segment's respective start and end points. The reason we, although feature extraction algorithms such as the line extraction algorithm provide additional computational cost to the system, the more compact parameterization of the line segment offsets that additional computational cost by allowing much less storage than the redundant laser scanner points that are the dense laser scanner points that are coming in. Moreover, the idea of data association, which is basically achieving correspondence between respective line segments, is much easier with features such as line segments, due to that, because there are more distinguishing parameters, and because of these parameters, which are less than the points, this also allows them to reduce the number of false positive data associations that may arrive in the system, hence providing a more efficient system. Our line extraction algorithm is basically such as this. Firstly, we take all the laser scanner points that come in from the system, and we initialize a fitted line across all of them. After that, we implement a split and merge algorithm, which was chosen due to its high speed and efficient computation. We go further into that. As we said, a line segment is parameterized by its angle and its radius. We initialize the line fitted line with the final point, as you see, YF denoting the final point of the points. Y and XF or Y and XI are the initial point coordinates of the set, which then we establish an estimation of the angle and the radius. The split algorithm is basically an iterative algorithm, which is basically, as we've mentioned before, we fit an initial line across all points, and then we check a distance as is seen from the photo on the top, the delta K. We check the distance from the delta K from each segment point across the line. The idea of the difference between the fitted line and the laser scanner points is as the photo below, with the straight line, with the line, the fitted line along with the dashed lines are the threshold in which we do not want the points to exceed that distance from the fitted line. After we check all the delta Ks that are respective to each laser scanner point, we check the maximum value of delta K, and we see if it exceeds that threshold that we have determined. If it does, we split the sets from before this respective point and after. Then we go and then we start the process all over again with these splitted sets. We keep on splitting until there is no delta K big enough that is across a threshold from each splitted lines. After we split each lines, we need to detect any collinear lines and merge them into one line in order to provide an efficient representation of the observation set. The two candidate lines are denoted as we know, the radius and the angle, with the difference in delta L, as we may see. Using a maximum likelihood approach, we provide a squared Mahalanobis distance that provides a distance that takes into consideration the covariances of the lines, along with the differences in the line parameters, and with a chi-squared merging criterion that we need to determine in order to provide efficient merging across the lines. We have the final step of the line extraction. After this final step, the new merge line parameters along with their covariances are created as follows. For going into the next step, we need a data association mechanism because the data set that was provided to us, there are no indices that, obviously with the line extraction that comes, there are no ready-made correspondences between consecutive lines, if we may say so. This step is very important into our basically the main algorithm, a main methodology that we have, which is derived from the iterative closest points algorithm, the ICP. However, we implement something similar, which is called the iterative closest lines, in which we take two sets of corresponding lines, and in order to not take the transformation, in order to not take the estimated poses from the odometry, as the odometry may have unbounded errors from the integral that are accumulated, we try to get the relative transformation from the iterative closest lines in order to get, as we see from the photo. After that, an iterative minimization of the error function happens through least squares. However, that will be explained later. This section is allocated to explaining our data association mechanism. Our criteria is basically this. We have two proximity-based criteria and two appearance-based criteria. The two proximity-based criteria, which basically comes from the merging criterion that we have already given from the Mahalanobis distance, in which we also need to provide a good enough criterion, p-squared criterion, in order to provide efficient merging. Moreover, we also provide a threshold on the segment endpoint difference between corresponding lines. The other two criteria that we provided is through the ratio of the lengths between corresponding lines, along with an overlapping criteria of the projected endpoints of one line onto another, in which the lengths of corresponding lines should not be too big in order to determine that these lines truly do correspond, along with an overlapping in which we know that these segments are not too far from each other along the same, in which two segments along the same infinite line do not match with each other. We limit this to overlapping lines in order to provide an efficient correspondence. We start with our main methodology of the iterative closest lines, which basically is derived from a least square from a Gauss-Newton algorithm, which is determined on a least square optimization. We have a cost function that we need to minimize, which is basically an error squared with the covariance which basically is given here. We need to determine an error function in order to get the error which is inside the cost function, which is basically a prediction function, difference between the prediction function and the observed values. We get the Taylor expansion of each operand in the cost function, which is derived as you may see here, the H and the B and the C. And all these gives us the final gives us the values of these matrices. Hence, utilizing the H and B matrices and differentiating the cost function with respect to the perturbation vector and equating it to zero, we have the following equation in which we obtain the minimum increment of the state, which allows us to improve the estimate that we have. Solving the main equation, which is H vector. In order to come back, in order to also implement the least square algorithm that we have, we need to also, except for the error function, we need the prediction function. And in order to provide the prediction function, we need to parameterize our state and our perturbations accurately. Our state is basic since we are deriving a pose estimation. We have a state which is a 2D isometry of the robot pose, a rotation matrix, and the translation vector. Which is a manifold here, not a Euclidean parameterization, as you may see. Our perturbation vector, however, is a Euclidean parameterization with the two translation vectors, as we are in 2D, and the delta theta. Utilize here in order to increment the perturbation with the state. However, due to the difference parameterization between manifolds and Euclidean and the Euclidean parameterization of the increment, we introduce a V2T function, which basically acts as integrating a Euclidean and a manifold together, which basically is an exponential mapping between the Lie group, which is basically the transformation, and the Lie algebra, which is the Euclidean vector of our perturbation. The prediction function, as we may see, which is the translated line parameters, the theta and the radius. The line parameters theta is theta plus alpha plus theta, and the radius is transformed as follows. It is to be noted that in our iterative closest lines, what we have is two consecutive lines, which have been corresponded. Hence, we have one that is fixed always, and the other one is the prediction function, which is applied, in which the translation vector, the transformation is applied onto. Which here is denoted by the superscript of f is fixed, along with the prediction function is the moving line. The error function, as we may see, is basically a prediction function minus the observation, which we have here determined. The final step, in order to get the H matrix and the B matrix, we need to get the Jacobians, which here we have a size of 2, 3, as the line parameterization is of size 2, and the differentiated with respect to the perturbation vector, which is of size 3. Finally, to go to our experiments, we have implemented the experiments using the C++ and ROS. Okay, we have implemented using C++ and ROS. The idea of using ROS was the data set was provided to us was through a ROS bag of the Aula Mania, along with the corridors of the first floor of the EC. We will show the line extraction along with the influence of the choice of the emergent criterion on the lines that come away. As we see on the left, we have here the laser scanner points, the raw laser scanner points. These two are through our line extraction algorithm. However, as you can see at the bottom, that's three different segments. This is due to a higher threshold of them. Which again comes back to we need an extraction algorithm that needs to be efficient enough in order for our iterative closest lines to work efficiently without much errors. We have another line extraction algorithm which also shows that sometimes it may not be accurate, as we may see. The middle one, which is of 10, is a more accurate representation, while the other one sees gaps and implemented the line segment, and so we need to be careful. At the other end, what we have here is basically on the left is a robot trajectory of the Aula Mania along with the corridors, based on the bedrock of the algometry. The line that is the line here with the circles in the middle, and basically the same corridor as the one previously visited. However, as I mentioned before, the unbound errors in the algometry have not been accurate. We will see from our estimated budget to the iterative closed lines. It's more rough than the algometry. However, as you may see, it's much closer than an algometry. To conclude, we have provided a line extraction algorithm, takes scanner points along with this noise model, along with the scanner points noise models into consideration, an iterative closest line mechanism that has been developed to estimate the robot trajectory, and the data association mechanism to determine corresponding set of inlier lines. The future work is a mechanism that is to determine previously visited landmarks to tackle loop closure more effectively. A global optimization of the mapping of the lines with respect to the estimated poses. But moreover, more complex features like blocks or curves may be implemented later and taken into consideration. I thank you all for your attention, I'll be happy to answer any questions.
Any question to Imam? Before, so I have one. So I think there are many line extraction algorithms, and indeed your interest here is in the context of SLAM. So you're looking at sequential images and how do you relate the information that you get so far in order to improve the next information. So can you specify what is the special contribution of your thesis in this field with respect to the state of the art?
The contribution thesis is basically taking the line, taking the layer standard, not an image, not such algorithm. The estimation of over of line segments. Moreover, data association scheme was implemented in various ways. However, taking the interacting criteria along with the measure, along with the T-square algorithm system.
Okay. Yep.
Thank you very much.
More comments? No? Yeah.
I'm sorry.
Independent from the order in which yeah.
Let me see. The first initial fit. Yep. No, it's as it comes. No, it's as it comes from the line scanner. We take it in the order that as it comes. So, yeah. However, all that position is the start and the end point of each segment. You shuffle the point as it comes. The line extraction does not do that.
Okay. So in a sense, you exploit the vicinity of sequential point. Okay. Fine. Yeah, sure. Thank you again. Let's. So next presentation will be by Amir Hossein Kazemipur. He's presenting his work on motion control of redundant robots with generalized hard inequality constraints. And I was his supervisor. Very good. Very good move. Can I start?
So good morning. Today I'm going to present my work about motion control of redundant robots with generalized hard inequality constraints. Starting with motivations behind this work. So we are interested in bringing the robots from an isolated environment inside the fences into human environments so that they can interact with humans or other robots to achieve collaborative tasks. Now, unlike a structured environment in which everything is known in advance, here there is an element of uncertainty. In fact, the robot has to be spontaneous. It has to respond to sudden changes in the environment and basically make decisions in real time. So in general, the robot has to deal with some internal constraints that may arise due to the physical limitations of the robot, or it has to deal with some external constraints that may arise spontaneously, which are typically expressed in Cartesian space. So our goal in this work is to propose a general motion control scheme that can handle these constraints online, both in joint and Cartesian space altogether. Now let us quickly review the state of the arts. So a conventional method for satisfying joint and Cartesian inequalities is to use artificial potentials, which can also be combined with some smooth activation functions. But the downside is that they usually suffer from oscillations, or they require parameter tuning to select the most appropriate parameters. As an alternative, we can use constraint optimization techniques, such as quadratic programming, by basically transforming the task into least square problems. However, these numerical methods tend to be computationally expensive, and they do not always give us a realizable solution. And finally, we have the saturation in the knowledge space, or SNS for short, which connects the quadratic programming to the stack of tasks approach and overcomes all these challenges. So in the original paper, the joint motion limits were treated as hard bounds that can never be violated. However, the hard bounds in the Cartesian space were not explicitly taken into account. Now let's move on. So here are the contributions of our work. So here we propose a generalized version of the saturation in the knowledge space method that explicitly takes into account both joint and Cartesian inequality constraints in a unified manner. Therefore, all the constraints have the same priority. And also, these constraints can never be violated, so they are treated as hard bounds. And we can modify, in fact, these constraints online and in real time without undergoing any parameter tuning phase in response to any modifications that can happen in the set of constraints. And finally, a key feature of this framework is, in fact, the optimal relaxation of a task when no feasible solution exists. So unlike quadratic programming, our framework can ensure the feasibility of a task basically by keeping its geometric direction, but giving away the timing law when no feasible solution can be found. So here we have proposed several algorithms, both at the velocity level and acceleration level commands, considering single task and multiple task control. And our final contribution is a new fast redundancy resolution scheme, which is much faster and efficient compared to the previous algorithms. Okay, now let's move on. Okay, so now let me briefly explain how we can combine joint and Cartesian inequalities all together. Let's say we have some limits on position, velocity, and acceleration for joints, and also for some control points that are distributed along the structure of the robot. Now, using these limits, we can shape the velocity limits to come up with an admissible range of joint and Cartesian velocities. And now we can introduce a generalized vector and an augmented matrix that can process all these constraints together. So in this way, we can come up with a generalized box of constraints that can be used in our framework to satisfy both joint and Cartesian inequalities in a unified manner. And so here is our first algorithm at the velocity level command, considering only single tasks. And now let me briefly explain how it works. So Inside this algorithm, there is a loop, and at every iteration of this loop, we check if any constraints are violated. And at the first iteration, the algorithm computes the solution using a standard pseudo-inverse approach. And based on this, if any constraints are violated, we put the most critical constraints to the saturation level and essentially repeat the loop until all the constraints are satisfied. Okay, let's move on. It is also possible to extend this algorithm for multiple task control. So given a stack of tasks sorted by priority, our framework can guarantee that all the tasks are executed, some of them with scaling, of course, but preserving the priority order in the stack of tasks. Okay, so we have validated our framework using simulations and experiments with different robotic systems. Here are the simulation results using a 6-hour planar manipulator. We have imposed some joint limits that are symmetric both in position and velocity. We have considered 5 control points with Cartesian constraints in the y direction at joint 2 to 6. So the primary task for the end effector here is to follow a linear path. And we also added an auxiliary task, which tries to keep the joint position as close as possible to the center of the joint ranges. And as you can see from the video, in both single task and multiple task control, the robot is able to completely perform the task while satisfying the Cartesian constraints that are here shown with dashed black lines. This is also evident from the evolution plots. As you can see, all the constraints in joint space and Cartesian space are respected, and in fact, many of them are saturated. And notice that also with multiple task control, the task error is greatly improved compared to the single task control. We have also validated our framework using experiments with the KUKA lightweight robots that we have in the lab. So in the first experiment, we considered a single control point at the elbow of the robot. And so we considered some fixed joint and Cartesian limits, and we also imposed some time varying constraints on the position of the elbow that are imposed only for some short time intervals. So as you can see from the video, the desired end effector task is to track a circle 3 times. And as you can see, the robot does a great job at fulfilling this binary task while satisfying all the generalized constraints. And you can see how well our controller reacts to the time varying constraints y direction. And finally, the scaling strategy that we have implemented, as you can see, keeps nicely the geometry of the path and therefore ensuring its usability. In the second experiment, again, we consider a single control point, but this time at the end effector of the robot. Here also we considered a more demanding task with a higher velocity to essentially bring the robot up to its physical limitations. Again, we imposed some joint, fixed joint and Cartesian limits, and also we considered the time-dependent constraints on at the end effector of the robot, with the position of the end effector. So as you can see from the video, here the desired end effector task is to follow a circle 3 times. And as you can see here, the time-dependent constraints that we have imposed, in fact, is conflict with the primary end effector task. So during this time interval, the end effector saturates to its limit to comply with the smart constraint. And in fact, as you can see, during the second round of the trajectory, the circle is nicely cut without showing any oscillations. Okay, so we have also extended the previous algorithm at the acceleration level command. This is in fact the most complex algorithm among all the ones that we have developed. We can use this in situations where the robot has to perform some dynamic tasks, or we can use it with an, for example, inverse dynamics controller to command also torque control robots. Okay, let's move on. We also validated our framework at the acceleration level commands, again considering a 6-star planar robot here. And as you can see again, in both single task and multiple task control, the task is perfectly executed. And also all the constraints are satisfied, as you can see from the joint space and Cartesian control point evolutions. And again, the multiple task control, the task error is greatly improved compared to the single task control. Okay, so the final contribution that we made was developing a fast redundancy resolution scheme. So basically, we came up with a simple rank 1 update formula so that we only need to compute the pseudo inverse of a row vector instead of an entire matrix at every iteration of the algorithm. So as you can see also from the plot, the execution time of this algorithm is in fact much faster compared to the previous algorithms that we have developed. So as conclusions, let me wrap up the main points. So in this work, we presented several motion control algorithms for redundancy resolution, considering joint and Cartesian hard inequality constraints. And the resulting control algorithms that we have developed in this work, in fact, can be regarded as a generic toolbox that can be used in a variety of robotic operations. In fact, the main advantages of our framework is performance and the ability to adapt to sudden changes in the time-varying part constraints. So as our framework can handle time-dependent constraints, we can use this and basically incorporate it into any sensor-based strategy, for instance, in human-robot collaborations, to prevent collisions between humans or other robots. And before finishing my presentation, I would like to thank my advisor, Professor De Luca, also Dr. Maram Khatib, Dr. Khaled Al-Khuder, and Dr. Claudio Gas for their support during this research. We initially submitted the basic concept of our framework in the IREM conference last year. And recently also we submitted another paper to the IEEE Journal of Robotics and Automation Letters, in which we addressed one of the algorithms that we have presented in this work. Thank you very much for your attention.
Thank you, Amir. Any questions? Yes. Yeah.
Exactly. So, yes. This is correct. This is correct, yeah. You lose in what sense? Okay, so basically, we do not relax the constraints in this framework. So we ensure that all the constraints are satisfied, so they're treated as hard bonds. And in fact, we assume here in this framework that the robot is redundant. So we have some degree of redundancy, that we can use this redundancy to satisfy the constraints. So if Exactly. So, in fact, exploiting the redundancy to satisfy these generalized constraints. And so it works very well for redundant robots, but I'm not sure if it's going to work with like underactuated or other robots, like underactuated robots.
Yes.
Thank you. That's in fact very good question. So our framework is in fact a local optimization technique in some sense. And so in fact, maybe a global method can come up with a solution that does not require any scaling at all. But since our method, I mean, we have to trade off between the computational complexity and local sense of the framework. But in fact, yes, it is possible that some global approaches give us the solution without requiring any scaling. And in fact, as you can see also, with the case of single task control and multiple task control, like the multiple task control didn't require any scaling at all, given the same priority, same task that we have defined according to the priority of the stack of tasks. So yes, it is possible that maybe global methods are handle these tasks better than this framework. However, Fabrice Flaco presented also, like within the SNS framework, presented an optimal version of this algorithm based on the KKT conditions, basically. So we didn't consider those into this framework, but maybe it is possible, like for future works, to also consider these situations and add those also. It will possible to add those lines like in the algorithms. It is just a few additional lines that can be integrated into the same framework, and then compare the results also with global methods and also like with this optimal version of this framework.
Okay, let me comment just that you show the first experimental video, which was flashing, but in fact, this was just the video. The robot was running smooth.
Yes.
In case you noticed that. Okay, thank you very much. Again. And next presentation would be remote. So we switch to, will be by Ali Najari. He's presenting a work on creation of reusable pipeline for synthetic dataset generation in deep learning-based automated claim management. And the supervisor is Professor Antonio Pietrabissa. So here we see, can we hear you? Can you speak up?
Yes, hi everybody. This is Ali Najari.
Hello. Can you hear us from the room?
Yes, Professor.
Because later on we will pose questions, so you should be ready to answer at the end. So you have 15 minutes now, please.
Okay. Let me share my desktop. Can you see? Okay, the title of my project is the creation of a reusable pipeline for synthetic dataset generation in deep learning-based automated claim management. Actually, this is a project thanks to Alice Innovation, who is working with Generali company on computer vision topics. In particular, they are working to leverage computer vision techniques to support claim specialists in the claim management process by extracting insights from images to allow them in making faster and more reliable decisions. Okay, at first, we are going to have an introduction and some explanation about synthetic dataset generation workflow. Then we see a 3D tool to create the model and its environment. We have some explanation about Blender workflow and post-processing and pipeline implementation for car model. Then we have a comparison between manually annotated and synthetic data set. And finally, we have experimental results and conclusion. Okay, regarding problem description, in car insurance companies are dealing with lots of insurance claims. They are using old manual claim validation that cannot handle the fast-paced need for insurance claim processing. The image collection is part of a standard process in claim management of insurer companies. Because of this, these companies are collecting every year more than 90 million images. Actually, these images have huge informative information, and they wanted to extract this information thanks to computer vision technology. This project has been started 3 years ago, while they had a great effort and resources into human-made dataset generation. Unfortunately, the preparation of this handmade dataset was cost-effective and really time-consuming. The main objective of this project is to create a kind of methodology, validate it, and implement a reusable pipeline to generate desired synthetic dataset as an input to the models in the image analytics ecosystem. To have a general view of the different steps of synthetic dataset generation, at the first step, we have 3D scene preparation. At step 2, we are going to render image and extract scenes information for labeling. There, the step is post-processing scene information to generate the dataset, and finally train image analytics model. At step 1, we are going to prepare 3D car model and 3D background, also simulate a random trajectory of a real camera path accordingly to generalize claim image. And in step 2, we are going to run the generation pipeline regarding different combinations and dedicate path indexes to panel and image labeling. In the step 3, merging annotation regarding a YAML configuration file is going to be done. Also, creation of a JSON file, which is responsible for our dataset. We are going to filter some noises from segmented image and visualize the annotation for a sanity check. And final step is comparing the trained model with the one in production in the IA ecosystem. Okay, for the 3D software necessities that we already choose a software which the name is Blender. We need to be able to simulate 3D objects, and also we need to have a camera to take pictures from different sides of our object. We also need to simulate the background and realistic floor during the segmentation, and objects, material, and photorealism are the other features which is really important for this project. In terms of the camera, as you can see in the left and the right picture, we are going to use 2 different methods. The first one is just create a camera and link it to the empty object in the middle of the picture. By use of this method, we are able to have an orbital point of view of the object. And with the, as you can see in the right figure, we are going to create a path, limit the camera to follow this path, and always track the middle of the scene to take the pictures from different sides of the picture. And also in the middle picture, we can see a sample of objects created in the Blender. Okay, in terms of simulation of the background and the floor, as we didn't want to simulate everything in the scene, for example, we didn't want to simulate a building, simulate trees and other stuff in the scene. We just used the 2D image, and by UV maps, we mapped this image on a surface like a dome, as you can see here in this picture. And with this method, we can avoid the background shifting problem with the creation of floors. And in terms of the segmentation, as you can see here in the kind of car model, image segmentation actually is a method in which a digital image is broken into various subgroups called image segments, which helps in reducing the complexity of the image to make further processing or analysis of the image simpler. And in the right figure, you can see a segmented image from the car model, which is a great image. And in terms of the material and color in Blender software, we can assign a material to every object in the scene to make it more realistic and have the ability to simulate some features such as reflection on the car body that has been one of the main challenges in panel detection process. Each material defines different features such as colors, metallicness, roughness, and other settings. As you can see here, the right picture is a simple one. By changing the material, the color, and other settings, we were able to create a car model that is really like a real car. And in terms of photorealism, the key to make photorealistic material is to reproduce imperfections. As you can see in the picture, we are able to easily simulate the reflections of the trees and the light, and also the different material that we use for the scene preparation, such as plastic, leather, and metal, you can see in this image. Okay, in terms of Blender workflow, we should have our 3D scene. Then we are going to define new path and set the camera to this path. We are going to enable a new car model, as we already have different car models in the prepared scene. Then we select a new background. There will be also different backgrounds, and we start the rendering scene with a specific color. Then we save render image as a JPEG image, and we start the segmentation process. Then we set the output directory and image labeling, and save all the segmented image as PNG. Then we change the camera location and orientation. If there is a new background, we will go through the other steps. If there is not, we go to the next step to enable a new car model. Then we go to other steps. If there is not any new car model, we go through the new path and other steps. When we have done all these loops, we are finished with the process of rendering. In terms of Blender software, we are using two main workspaces. The first one is scripting, and the second is compositing. In the scripting part, we are going to do read configuration file, dedication of path indexes, camera initializing, rendering 3D, scenes, and random path creation. In compositing part, we are doing access rendering layers, mask IDs, segmentation, compact all segmented parts in a gray image, and save all the segmented image. And in a scripting workspace of the Blender, we have a configuration file. This file is a CSV file that all the car parts with a standard name is there. We are using these names to find the related object in the scene. Then we go to dedication of the path index. The camera position and orientation can be modified with two different methods. One is orbital point of view, and the other is define a path and set the camera to follow this path. In the final version of this pipeline, we are using the second method. In the rendering part, we are choosing the quality and the output format of the 2D image plus the directory. We are going to save the rendered image in this step. And a spiral shape path is also created with the scripting code that has some random parameters to prevent similar camera point of view. And in the compositing part, at first we need to have access to rendered image from render layer node. Then we go through grayscale segmentation in compositing workspace based on object path index. And mask IDs are some nodes in compositing workspace that let us to find each panel of the car. The output of this block is white and black images. Then all these white and black images need to be compacted to a gray image. We are going to do it in the next step. And we also need to define a directory and a new name for every rendered image for a scripting part to prevent overwriting. For the post-processing, we need to read necessary directories, read the YAML configuration file, and consider necessary annotation merging. Then we open main directory and read the rendered image. At the next step, related segmented image should be read. By reading this segmented image, we are able to generate all the information which is necessary for our larger scale data set. Which one? That the first one is polygonal annotation, bounding box annotations, image IDs, and category IDs. Because of some problem that we had with noises in segmented image, we had to create a kind of filter to filter segmented area lower than 25. If this area is lower than 25, we do not consider annotation. If it is greater than 25, we append the information and go through the other steps. And finally, we will create a JSON file which has all the information related to our COCO dataset. Actually, we used this pipeline for implementation of a car model. This pipeline already have 12 different models of the car. Each car consists of 63 panels and 37 different backgrounds. These backgrounds are responsible about different lights, shadows, weather condition also will be considered in these backgrounds. And we also have 21 different specific realistic colors. I will show you in the next slide. And the complex camera path with ability to change randomly to prevent repetitive car image. We also have 4 different average distance of camera from the car. And the rendering image resolution is this, and 16 main categories are defined for this data set. You can see also in the right picture different panels of this car model. And these are also specific colors we defined for this version of pipeline. And different car models you can see here in this slide, which are 12 car models. After generating everything, after preparing the data set, we needed a sanity check. Because of this, we developed a code, just a sample of annotated car model that we just check that every segmented part is going to be segmented in the correct way. And in terms of the comparison between manually annotated and synthetic data set, in utilization simplicity for manual annotated data set, there are advanced tools for speeding up the annotation process, but in the synthetic data set, there are some general purpose open source framework. In terms of annotation type, we had experiment with 4 data scientist experts. They were successful to complete the process of annotation in 17 minutes per second, but we are going to do this process with synthetic data set in just 15 seconds. And in terms of robustness, manually annotated data sets are prone to errors, but in synthetic data set, we can freely generate as many situations as we want. And in terms of the experimental results, we use the generated data set with this pipeline and kind of deep learning method, which then the name is RCNN method, is implemented for the car panel detection with the setup in this table. And as you can see here, for the mixed data set of 5,000 images, we were able to improve the final results of this panel detection method. And these are some results about this panel detection algorithm. As you can see, the method was able to detect different panels of the car with a kind of precision. And in terms of the conclusion, we developed a methodology that has been that is going to generate a reusable pipeline. This methodology has been validated with the generation of a synthetic car dataset. Human label datasets are expensive and time-consuming. We can complete this time-consuming and costly procedure in the shortest amount of time. And also a mixed dataset of human label data and synthetic dataset can gain better final results. All the pipeline also is implemented on the cloud. Thank you for your attention.
So, could you come back on video, Ali?
On the
You should unshare the presentation.
yeah, I shared the presentation.
Stop sharing. The green button below.
Oh, okay.
Okay,
Sure.
fine. Okay, so thank you for the presentation. Are there any questions? Yes. Yeah, go to the mic.
All right. So, hi again. Thanks, Ali, for the presentation. I have some, so first a question to understand and then a question on the frame. The first question is like, so basically the key idea is that you load a model into Blender, then you define a path, you render a lot of images of this model with varying parameters of material, and then in order to generate labels, you basically change the materials into something which renders into an opaque color or something that is easy to identify. And then for each picture, you generate a pair, one containing the image and the other one containing the color-coded labels. Is that right?
Exactly, yes.
Yes. Okay. Now, the question is, this is wonderful. I mean, it's a nice idea that works with when you have a CID model of the object, right? And then my question is, how would it work with something for which you don't have a precise CID model? Let's imagine a person or a cloud or a plant or something which is a little bit more articulated. So for which there is no nominal model. How would you expect this to scale? How would you address it with your frame?
Actually, this process is going to work with some items that we can model it with a 3D software. And if we are not able to model something in a 3D software, it is not going to work.
I didn't understand. Sorry, I mean, the audio wasn't really spectacular. Could you repeat?
Yeah, sure. Actually, this method is used for the objects that we can model it precisely. And this precision is really important for us because we need to create a real something like a real model. Without it, it is not possible to have good results.
Thank you.
You're welcome.
Okay, thank you very much. It's difficult to interact in this way, but at least you replied to one question. So thanks again.
Thank you so much.
So we go back to a presentation in presence. Sabatucci. So switch. Huh? So Samuele Sabatucci is presenting a thesis on biologically inspired modeling of continuum soft robot manipulators. I was his advisor. And you should also switch back to, okay. Okay. Okay, fine.
So good morning and welcome to the presentation of this work based on biologically inspired modeling for continuum soft robot manipulator. If we think about classic robots, they are not all similar to biological system. In fact, animals' body compared to rigid robot look overly redundant, imprecise, and weak. In fact, many biomechanics studies have pointed out to elastic and compliant element as a fundamental ingredient to explain the gap that animals can still perform a vast range of activities with unmatched effectiveness. In this work, we consider a new design for a continuum soft robot inspired by an octopus tentacle. The aim is to achieve both bending and elongation in the 3D space. Finally, the body of the robot is modeled under the piecewise constant curvature assumption. So if we consider the octopus, they are a great example of dexterous animal that we can find in nature. In their arms, the muscular structure is organized mainly into 3 groups. The transverse muscle for elongation, longitudinal for bending, and oblique for twisting. What we do is we merge the elongation and the bending features in 4 pneumatic artificial muscles able to change in length. Commonly, in the state of art, a cylindrical structure is used in order to replicate a biologically inspired segment. However, we have to consider that in nature, octopus tentacle has a tapered angle. So here we come with our design for constant curvature actuators displaced every 90 degrees that can change in length and elongate the structure of the segment, changing the tapered angle. But to describe what happens when the tapered segment bend, we need at least 3 variables. Phi, the angle between the plane NO and the curvature plane. Theta, the relative rotation between 2 reference frames on the bending plane. And delta L, the change in length of the backbone segment. And we are going to call this choice of the variables as the alpha parameterization. Moreover, the tapered segment is advantageous for the arm's mobility since it allocates more torque to the segment closer to the base. However, introduce a quite difficult challenge since the 4-arc bend on non-parallel planes. We solve this issue with an exact geometric solution that gives us the length of each cable when the segment is bending as a function of the alpha parameterization. Here we can see a tapered segment while it is bending and performing a rotation around its central axis. And thanks to the formula discovered before, we are able to describe the posture of the backbone in purple of the segment. So entering the kinematic modeling, a piecewise constant curvature robot is composed by a fixed number of segments continuously deformable with a curvature that is constant in space and variable in time. The homogeneous transformation matrix T maps the posture of 2 consecutive reference frames, and we can give it a geometric interpretation since we can consider it as a rotation around the z-axis of an angle phi times the multiplication of a row to translation until we reach the next frame on the top of the segment, and then we come back in the original framework of a rotation of minus phi around again the z-axis. But the alpha parameterization is affected by mainly three problems. First of all, the straight configuration can be described by an infinite choice of the variable alpha. In fact, the homogeneous transformation matrix is not an isomorphism. That means that we could wrongly think that keeping constant the angle theta to 0 and varying the angle phi, we could generate motion, but that's not the case. Second, as explained by the bullet B, two different configurations that share that properties describe the same posture. And finally, closeness in the task space is not equivalent in closeness in the configuration space. But how to solve this issue? In fact, it's just a matter of parameterization. If we choose to project the angle theta along the x and the y axis, we solve all three issues. And we're going to call this parameterization the Q parameterization. For what concerns instead the control input for the each segment, we consider the branches composed by tau x, the torque around the n-axis, tau y, the torque around E, and the force along the O-axis. However, we have to consider that it's not possible to exert branches directly on the acceleration, so we need an input mapping A. And since the branch is internal of the segment, we have to consider that an opposite, at the previous link, an opposite branch is appears. Then, by means of an Euler-Lagrangian approach, we derive the dynamic equation of motion. For what concerns the simulation, we consider a two-link soft robot manipulator of equal length of 0.4 meter, but different masses. So the first link is 0.5 kilogram, instead the second one is 0.4, and the table summarizes the parameters for damping and stiffness for the robot. And each simulation that we're going to see will last 30 seconds. So we start from initial configuration that is straight facing downward, that recall was a singular configuration for the alpha parameterization. We will plan in alpha and then we will move to Q just for a matter that alpha parameterization is meaningful with respect to the direct representation of the posture of the robot. We're going to see two simulation scenarios. The first one will address the shape control of the robot, and we are going to use a control law composed by a PD plus a gravity cancellation term. For what concerns instead the last two sets of simulation, we are going to address the trajectory tracking problem, and we are going to use a feedback linearization control law. So for the first simulation, we ask the robot to reach two different configurations, alpha 1 and after 15 seconds, alpha 2. Recall that we have to move to the Q parameterization and compute Q1 and Q2. And as we see from this plot, the evolution of the configuration quickly reached the desired value. And after 15 seconds, the references change. And after a small transient, the robot achieved the task. So here we can have a visualization of what is happening. So from the first picture, we see the first 15 seconds. In blue, it's the initial configuration. The robot is starting from a straight facing down configuration and then quickly moves to the first configuration in red. Then in the other plot, we start from the previous configuration and we reach the final reference in purple. Here we show the input, the evolution of the input and the error that, as we can see, quickly go to 0 and at 15 seconds change to reach again the value of 0. So now we are going to consider what happens if we add a disturbance, the red arrow in the first plot, at 80% length of the second link from a t-start of 17 seconds until 18 seconds. And as we can see from the second image, we see how the robot responds to the disturbance and then come back to the purple configuration, so the desired final configuration. Here in the gray area, we see the time in which the disturbance act and how affect the evolution of the configuration. And also this for the input and for the error. Now, for the second scenario and the third simulation, we ask the robots to move from a configuration alpha 1 and reach a configuration alpha 2 using a specific trajectory. And we're going to compute the specific trajectory in a Q as a quintic polynomial. As we can see from the plot, the robot followed the desired trajectory for all the time of the simulation. As expected, the error is always zero, since the feedback linearization control law cancels all the dynamics of the robot. Here again, we see the robot starting from the initial configuration in blue and reach after 30 seconds the final configuration in purple. And here we can decide the timing in which this happens and the path that the robot has to follow. Here we see how the robot differently behave when the same disturbance act at 80% length of the second link. In fact, we see that the robot starts to oscillate when the disturbance acts. So the red arrow again is the disturbance acting on the robot, and we see that the robot starts to physically oscillate until it comes back to the desired configuration. These reflect also in the error and in the input of the system. So to conclude, we have presented a new design for a tapered, pneumatically actuated, soft robotic arm. And this work represents a great example of biomimetics. That means the translation of biology into robotics. We have validated the model in 3D environment for a PCC soft robot while performing bending and elongation maneuvers. For what concerns further development, there are open challenges in sensing and proprioception, and moreover, we could add twisting features, and more important, there could be a model extension to include also a carried payload. Thanks for your attention.
So, very good. Quick presentation. Any comment on this? Yes.
Now, the motion is belongs to a 3D environment. So the robot is divided into segments, in this case, 2 segments. Each segment can bend in all the direction and can elongate its structure. Because we don't consider the twisting maneuver and in the model. So we just consider that when we move to the when we consider the segment that bend, we see that the bending does not affect how the orientation of the top reference of the segment. That's features that could be had in the following up of this work. Yes, it's exactly that.
It could be, it's a plane, but could be any plane. Okay. In fact, it is correct to say that you can have one bending plane for the first segment and a different bending plane, so that you get torsion through the segments. Between segments.
Yes, between the 2 segments and have different bending plane.
Not within the segment. Sure. Stays. More questions? Okay.
Okay. As you've seen in the simulation, they're not described all the body of the robot, but just the backbone. So when we add the disturbance, we are considering that this is the equivalent disturbance on the backbone of the segment. It's not a real disturbance on the body of the robot. So this is the answer to your question.
One more question.
Okay, so I got the question. So basically, the state of art divide in two different opinions. First one, they try to replicate rigid robot as a soft arm. Instead, you could choose to place the center of mass in a specific place, like for example, the half of the cord of the robot. But however, this is not replicate exactly the position of the robot. It's just an assumption. Instead, in this case, you model the segment as a sequence of parameterized position, and then taking advantage of the Jacobian that maps the angular velocity of the configuration Q and the angular velocity of the position X, you basically is an integral that compute all the configuration and when the mass is not equally distributed, you can compute an exact position of the center of mass for the segment. Now, since it's a tapered segment, it's not uniformly distributed like a cylindrical one. Yes.
Okay, thank you again. Next presentation is by Leonardo Salustri. He's presenting his work on fault-tolerant control of a tilted X-rotor UAV, and the supervisor is Professor Andrea Cristoforo.
Just one moment, sorry.
Okay.
So good morning, everyone. My name is Leonardo Salustri, and under the supervision of my advisor, Professor Andrea Cristoforo, I developed my thesis work about fault-tolerant control of a tilted X-rotor UAV. In recent years, fully actuated multirotors have gained certain popularity because they can overcome the intrinsic limitations of classic collinear multirotors. The full actuation property can be achieved through two different design concepts. The first, which is the one of interest for this work, is the fixed tilt concept. In this case, the multirotor is equipped with propellers which are generically tilted with a fixed orientation that cannot be changed. In the second case, with a variable tilt concept, the multirotor is equipped with additional actuators other than the propellers, which are going to actively control the propeller's thrust direction. The fault-tolerant control problem is the problem of controlling the multirotor, dealing with possible faults of the component. The objective is to propose an active control strategy in order to address both light and severe faults when the X-rotor is asked to follow a trajectory. It is active because it is based on a chain of two fundamental tasks: the fault diagnosis, which gathers the information about the fault, and the control reconfiguration, which accommodates the fault on the basis of this information. This work is inspired prevalently by the two papers, which are reported in this slide. In particular, the fault diagnosis module is implemented using the observer defined in the first paper, which is adapted to use an attitude representation in a special orthogonal group, SO3. Moreover, if a rotor fails completely, the control strategy presented in the second paper is modified in order to allow the accelerator to continue the trajectory tracking task. We are focusing on a particular family of accelerators, the alpha, beta, gamma accelerator. In fact, since the eye propeller is generically tilted, its orientation and positions are parameterized by the angles alpha, beta, and gamma. As we can see in the top figure on the right, these three angles represent the rotations around the three axes, X, Y, and Z. With the choices made for this work, which are reported in the red rectangle, the accelerator is considered with the propellers which are placed on a plane, the XY plane of the body, with a star configuration. The thrust is developed along the ZPI direction that we can see in the figure below. And this is determined by the angles alpha and beta in particular. So from the Newton-Euler equations, we can see in the first rectangle, we can derive a dynamic model where the position P is the position of the center of mass of the drone, B is the translational velocity of the center of mass, and as previously said, the attitude is represented in the special orthogonal group through the rotation matrix R. The angular velocity is omega expressed in the body frame. So the inertia matrix J is diagonal. Moreover, in a realistic scenario, we would have inputs to the system, which are aerodynamic disturbances, external disturbances, and the gyroscopic torque. Moreover, in the equation, there is the appearance of the branch, which is Fc tau c, so the torque of force and the vector of force and torque delivered by the fact that the propellers are spinning. So we are considering the actual control input U, which is taken as the square of the spinning rates, and it is mapped to the branch to the input allocation matrix F, which is divided in F1 and F2. F1 maps the input to the force, and F2 maps the input to the torque tau c. Moreover, since we are dealing with faults, there is the pre-multiplication of the input U by this diagonal matrix W, which is made of the weights. Wi, in fact, is the height multiplicative weight, which represents the faults on the eye rotor. Through the study of the input allocation matrix, we discovered that the healthy accelerator is uncoupled before fully actuated, while instead the accelerator with a loss of a rotor or two opposite rotors has a single decoupled direction. Decoupled means that the attitude and position subsystems are decoupled one another. In fact, we can define a direction which is called the preferential direction B, which is in the kernel of F2, so the null space of the F2 matrix, and these can be mapped in the force space through the F1 matrix, defining B. The idea is that acting along B with the control, we can develop a force along B in the body frame, which does not change the attitude. The assumption made for the control is that the state is available at any time, the gyroscopic torque is negligible, and the actuator's dynamics are smooth transient, therefore we will not include the low-level control. Here we can see an overview of the general control scheme. In particular, below, there is the fault diagnosis block, which provides an estimate of the multiplicative weight, W hat. On the left, this vector is tested in the logic condition. If all the components are greater or equal than some threshold T, then the FA control law, which stands for fully actuated, is enabled and tries to preserve the full actuation of the accelerator while dealing with live faults. Instead, if a component is less than the threshold, the control law is switched to the under-actuated control law. Here we can see a detail of the FA control scheme. In particular, on the left, we have the references down to the acceleration level in terms of attitude and position. Then we have two blocks, the attitude stabilization and position stabilization blocks, which provide the high-level commands in terms of torque and force. The torque tau c is developed using a geometric control on the special orthogonal group, while Fc, the force, needed for the position control is a PD plus gravity cancellation. The control allocation on the basis of the estimate coming from the fault diagnosis will deliver the actual control to the accelerometer, U. As previously said, the fault diagnosis is implemented using a nonlinear disturbance observer, lambda, which is, whose expression is in the first equation in the slide. We can see that there is the appearance of the H matrix, which is a diagonal matrix made of gains, which determine the convergence. Defining the estimation error, W tilde, which is W, the ground truth, minus the estimate, its dynamics is a linear time varying dynamics with input W dot. So we can prove that the estimation error is bounded. And for this reason, also the closed loop system, it can be proved to be ultimately bounded. Moreover, another important result is that the control system is converging input, converging state, so CICS, with respect to the estimation error. This means that if the estimation error goes to 0, then the tracking errors also will converge. In the case of a loss of a rotor or two opposite rotors, we have an underactuated system, so the control law is switched. And in order to prioritize the position tracking, we are using a nested feedback control structure, a classic one, where the position control will drive the attitude subsystem through the generation of a planned attitude represented by RP, the rotation matrix. This rotation matrix is aligning the preferential direction D to the desired force, which is needed for the preferential for the position control. This means that D is conceptually similar to the upwards direction in case of classical linear multirotors. Now we can present the simulation, and in particular, we can see in the table the parameters used in this case. For what concerns the trajectory, in terms of position, we are tracking a spiral, while instead for the attitude, we are a fixed attitude reference, which is the identity. So rho PTO angle is equal to 0. Default instead is modeled as a trapezoidal time law, parameterized by these two parameters, S and delta T, where S represents the severity of the fault, and delta T instead is the interval of time in which the fault drops from 1 to 1 minus S. The first case is the light fault case. So we introduce a light fault of severity 0.2 on the third rotor. In the plot, we can see the ground truth and the estimate performed by the nonlinear disturbance observer. During the transient, it's clear that the estimation is bounded but non-zero, while instead, at the end, when the fault stabilizes, it converges. In particular, we propose a comparison between a non-fault tolerant control and the fault tolerant control proposed in this work on the right. So on the left, we can see that the tracking errors in terms of position error norm and attitude error are bounded but non-zero. They are bounded obviously by because there is the feedback action. While instead on the right, we are able to converge to 0 because of the CICS property mentioned before. Also, in terms of control efforts, so the spinning rate of the rotors, on the left, we can see that since the height component, so the third rotor, is not isolated, the error is distributed among all the rotors. While instead, on the right, the third rotor is isolated by the observer, and therefore it is increased in terms of spinning rate to compensate for the error. We can also see the 3D trajectory plots below, where the red dotted line is the reference, and instead the blue line is the actual trajectory of the accelerometer. The other case that I want to propose is a severe fault case. In this case, the severity is 1, so we have a complete loss of the third rotor. Again, here we can see that the estimation error is bounded during the transients, and moreover, when the estimate reaches the threshold T, which is 0.3, the estimation stop, in particular, the third rotor will be considered failed, and the opposite rotor, so the sixth, which is the blue line, will be switched off. This is part of the underactuated control law. Here we can see on the left, in particular, the tracking errors, again, in terms of attitude and position error norm. Moreover, it is interesting to see that when the control law is changed, and this is pointed by the red arrows, there is a sudden change in terms of roll PTO angles and attitude error. This is because since the control law is changed, we are tracking a different attitude, so a planned attitude, and this is a discontinuity. This is clear also from the spinning rate plot, so the one on the bottom right, where the FA control law, we can see from the occurrence of the fail, which is indicated by the dotted black line, the third rotor is increased in terms of spinning rate due to the FA control law in order to compensate for the fault. But when the threshold is reached, this is considered failed together with the opposite rotor, which is switched off. The other 4 remaining rotors will track the position and stabilize to a certain value, which is dependent on the preferential direction. We can also see, in this case, a 3D trajectory plot in which we can see a slight deviation from the reference when the fault occurs. So the proposed control scheme is able to identify and accommodate simultaneous light faults. It achieves good performances even in presence of a rotor loss when the position reference does not have abrupt changes. So we require the position reference to be smooth. The convergence is also highly dependent on the velocity of the fault, because if the faults act very quickly, the initial conditions when the control law is changed are more challenging for the control. Possible improvements could be the inclusion of the actuators model, or we could find the bounds for the position trajectory in terms of its velocity and an estimate of the region of attraction that assures the ultimate boundlessness property of the failed hexarotor. Moreover, we could implement the nonlinear disturbance observer also in the failed case. These would allow to tolerate, to bear also faults, light faults, on the 4 remaining rotors. Thank you for your attention.
Any question for Salustri? I don't know if you happen to follow the seminar of Antonio Franchi that was given here.
No.
So in any case, I'm posing a similar question that I posed to him. So one strategy, once you recognize that you have a failure of one of these thrusters, is to switch off the opposite one, which seems like, you know, you already given up one. So why you're doing this? Is this the optimal way of doing? What is the criteria of doing this?
Well, the idea is that if we have a fail on a rotor, we remain with the 5 propellers available. And these would generate, thanks to the drag torque, which is generated by each of the propellers, an imbalance in terms of symmetry of the control. While instead, if we switch off the opposite rotor, we remain with an even number of propellers. And therefore, the preferential direction, which can be found in the kernel of the F2 matrix, is balanced, is symmetrical with respect to the 4 remaining rotors. And this can be seen for this plot, the spinning rate plot, where the 4 rotors will stabilize to a value which depends on this direction. Instead, if we have the 6th rotor, so the blue line available, this would be, would stabilize to a value which is close to 0, because it has to compensate for the drag torque. And this could lead to problems in terms of saturation of the rotor. When there is a certain torque asked, for example, at the beginning, or when the control law is switched.
Okay. So you are exploiting the symmetry of the system.
Yes.
So what if you have a pentarotor and you're switching and you have a failure, then there's no opposite.
No, in that case, it it depends obviously on the tilting angles of the pentarotors and the study of the kernel of the F2 matrix. The idea is to find this preferential direction. Everything is based on that.
Okay. More questions? Yes.
Yes, is okay. So why it has a sinusoidal wave? Okay. Yes, the idea is that we are fixing the attitude to the reference one, which is the identity. So all PCO angles are 0, and we are delivering a force which will point in the direction of the spiral. So this will require the rotors to oscillate at the beginning, while instead, when the actuation, the under-actuation is exploited, we have a torque which is 0, a required torque which is 0, and the delivered force is along the direction which is needed, which is the preferential direction. Okay.
Okay, thank you very much. Again.
Thank you.
And our last presentation will be by Giuseppe Cinzolini-Arra. His work is on distributed nonlinear MPC for real-time navigation of multi-agent system in forest-like environments. The supervisor is Professor Giuseppe Oriolo. Please.
So good morning, I'm Giuseppe Cinzolini-Arra, and I present distributed nonlinear MPC for real-time navigation of multi-agent systems in a forest-like environment. The advisor of this thesis is the Professor Giuseppe Oriolo, and the co-advisor is Barbara Barros Carlos. Multi-agent systems have become increasingly used for a wide variety of applications, and in many cases, these robots have to navigate through complex environments while staying in a desired formation or while accomplishing many different kinds of tasks. To accomplish these tasks, we have a huge variety of control techniques. And among all available control techniques, nonlinear model predictive control is really emerging as a popular choice. For this reason, we need the algorithm which needs to be fast, distributed, and robust. The thesis will address, first of all, the description of the agent dynamic model, and then we proceed by introducing the control objectives and basic concept about distributed control. And after two assumptions, we describe the real-time NMPC and the Lagrange multiplier method, which is a novel idea of this thesis. The presentation will conclude by showing some simulation scenarios. So the formation we are considering, the agents we are considering are basically quadrotors actuated by brushless motors. And the quadrotor state variables are the position vector p, the orientation gamma, the velocity vector b, angular rates omega, and propeller's rotational speed capital omega, while the inputs are motor torques. So the nonlinear dynamics of an agent is represented by the first order ordinary differential equations, which are shown in this slide. I will not go into details of this formulation of this dynamic model, but it is important to notice the complexity and the high nonlinearity of this model. Given a multi-agent system specified by initial and goal position for each agent of the formation, and given an environment which may contain static obstacles, we would like to use nonlinear model predictive control in order to obtain suboptimal control inputs for each robot of the multi-agent system. And this is done by solving a constrained multi-objective optimization problem at each sampling time. Also, for each agent, we would like to avoid any collision with static obstacles and with other agents, while minimizing a multi-objective cost function and respecting the physical limits of the quadrotors. the nonlinear model predictive control is implemented in a distributed way because we acknowledge the limitations of centralized approaches. And so we use distributed nonlinear model predictive control in order to have a scalable solution with respect to the number of agents in the formation. The formation is defined by using standard graph theory concepts, but here I want to focus on the idea behind the neighborhood set. So we define the neighborhood set of an agent M as the NN closer agent to the agent M itself, where the distance is measured through Euclidean distance. Few assumptions are necessary. First of all, we assume that the state is measurable through embedded sensors. The state estimation and input equation are not considered to be affected by any noise or source of uncertainties, and each agent can detect the position of the other agents through direct communication, and we assume this communication to be ideal. Also, the position of the static obstacles are assumed to be known a priori. With this in mind, we can introduce the optimal control problem, which is a classical one, and we have this continuous time optimal control problem, which is formulated by, as shown in this slide. So we minimize the cost function subject to some constraints. In particular, we impose an initial state. We have some continuity constraint based on the previous mentioned ordinary differential equations. And we have path constraints and terminal constraints that will be addressed later on. We have to mention that this OCP cannot be implemented as it is, but we need some discretization techniques. And in particular, we will use direct methods. So the constraints of this system are various. So first of all, we have physical limits of the motor. So we have the input torques, which are bounded in magnitude. Then we have the collision avoidance. We define collision avoidance with respect to static obstacles in the environment, which will be basically forest-like obstacles, so cylinder going from floor to ceiling. And we define a safety distance for both based on the physical parameters of the quadrators and of the obstacles. And we also enlarge these distances by using an epsilon. So we formulate the collision avoidance soft constraints as shown in this slide, where SO and Sn under bar denotes slack variables of proper dimensions. Lastly, we have the collision constraint in the sense that we want to penalize, we want to constrain the system to be closer than a certain maximum communication distance, which is denoted by D bar AA. So the cost function is the summation of various terms. We have, of course, a tracking error penalizing the error with respect to the reference trajectory. We have a control error penalizing the error with respect to the reference control. And then we have a cohesion term, which penalizes the distance, the error distance with respect to the nominal one, where the MJ denotes the Euclidean distance between agent M and agent J. And lastly, we have a constraint violation term penalizing the violation of the soft constraints by using L2 norm and L1 norm. Finally, the optimal control problem is depicted in this slide, where we're summing up all the terms of the cost function and we impose all the constraints. In particular, we have the initial value constraints and the dynamics, which is integrated with an implicit Runge-Kutta method of the first order. And we, of course, have physical limits and collision avoidance constraints. This method is this optimal control problem is discretized by means of the direct optimal control, and I will not go into details here, but it is just important to notice that the cost function and the pi, the function g that collects all the equality constraints, and the function h collecting all the inequality constraints are subject to some smooth assumption about smoothness. There exist different methods for to address this problem, and we use direct multiple shooting. First of all, we select a time grid, which is non-uniform in our case, because we claim that this kind of grid, which is depicted here, is able to guarantee a little bit of extra robustness with respect to a uniform one, and it is also well suited for future works. We also introduce we discretize the controls. We numerically simulate the ordinary differential equation. After that, we impose continuity constraints, and we discretize inequality constraints, HI and HF. And so with the multiple shooting time NLP, we can proceed by using sequential quadratic programming in order to solve the problem by solving at each iteration an inequality constrained quadratic program, which is an approximation of the shown NLP. Lastly, we have the Lagrange multiplier method for online multi-objective and constraints prioritization. The idea is that since we have conflicting objectives, we would like to activate the weight omega bar, which I remember is the weight inside the cohesion term of the cost function, and we would like to update this term at runtime. Therefore, we making use of the Lagrangian function, we derivate this Lagrangian function with respect to omega bar, and we obtain an ideal update law for this vector, where with mu we denote the Lagrange multipliers associated with an inequality constraints of the agent of an agent M at a shooting node I. So some implementation details. We assume as an agent obstacle safety distance DAO of 1 meter, while the agent-agent safety distance is 0.9 meters. And an important value here is the sampling time of the system, which is 20 milliseconds. Therefore, our implementation should stay above this threshold. And the whole framework is implemented in Python using the Akatos package to address the NLP formulation, while the QP arising from the NMPC are solved using a high-performance interior point method, which is a state-of-the-art solver. So the first scenario deals with the collision-free position swap. So we have an octagon-shaped formation performing a collision-free position swap, and the idea is that we want to stress the agent-agent collision avoidance. The agent-agent collision avoidance, and so this scenario is really challenging from this point of view, and it returns useful metrics for the tuning. In particular, we concentrate our attention only a few of them. We can measure the solution time for different number of shooting intervals and for different formations, and we can observe that the system is well below the threshold of 20 milliseconds, and it is highly scalable with respect to the number of agents because of the distributed implementation. And also we notice here that the size of the neighborhood set is quite important because it is directly related to number of constraints of the optimization problem. At the right, we can show the worst measured distance among all agents for different value of the penalty, slack penalty value, alpha under bar n. And we have that, we can find an optimal value, but we can notice that there is no benefit in higher values, extremely high values of this penalty term. The second scenario is the collision-free navigation in a forest-like environment. We define a formation which is rigid, and it is a straight line formation. We use 150 different environments containing different kind of obstacles, different occupancy rate. And we evaluate this scenario based on solution times, collision avoidance, success rate, and quality of the trajectories. And from the picture at right, we can notice that slight violation are present in the agent-agent distance, but they are really minimal and therefore acceptable because below the threshold of collision. And the same holds for the agent obstacle distance. So this is a simulation from a top and a lateral view. And here we can appreciate the dynamic update of the neighborhood set. And we can also show the how close to the violation are the constraints. by means of this sort of heat map. And when the links become yellow, it means that there is a violation, but it is possible to notice an aggressive reaction of the system in these circumstances. So as expected, we have that collision avoidance is worse for high occupancy rates of the environment. And on average, we have that the Lagrange multiplier method improves the agent-agent collision avoidance and the agent-obstacle collision avoidance, at least for high occupancy rates. And the average solution time is between 1 and 2 milliseconds, which is coherent with our sampling time. In conclusion, the proposed approach leads to satisfactory performance in terms of solution times, success rate, and collision avoidance. And after more than 1,800 simulations, we have some statistical results proving the robustness of the proposed approach. Also, the distributed approach, together with the use of the neighborhood set, makes the system highly scalable with respect to the number of agents in the formation. And the Lagrange multiplier method slightly improves the performance. Future improvements may come from the introduction of communication blackouts, or from the use of high-level reference trajectory, or by testing other more complex formations. Thank you for your attention.
Question for Sensorini? Sure.
Yes. Exactly. Yes, exactly. As shown in this slide, we use we prove from here that you can see the legend. Maybe I don't know if it is too small, but for a formation of two agents and only one neighbor, we obtain a really lower solution times. This proves that the neighbor's size really affected the computational time, and this is why we constrain the neighborhood set to be not more than 3 or 4 agents, which are, of course, exactly, yes. Yes, yes. Exactly.
Yeah.
Exactly, sì. Yes, but it is mostly related to the idea of using sequential quadratic programming, because we don't solve the problem, the optimization problem up to convergence, but we only solve the first iteration, and this is the idea, the reason because it is a suboptimal solution. Mm-hmm. Yes, of course, it is suboptimal. Of course, of course. Yes, absolutely. And yes, absolutely. The size of the neighborhoods is really important, and it is one of the reasons because we say that it is a suboptimal solution, and we found this set to be really important. So 3 or 4 agents appear to be a good size for this neighbor, at least for this formation.
Okay. Then thanks again. So we'll be very quick in deciding the final grades, but I have to ask you to go outside for one moment. 5 minutes, 10 minutes, and then we will resume for the proclamation. Here. Emami. Emami. You should come here. Is Ali Najari also connected from home?
Yes, Professor.
Okay, good. So, the following student candidates have passed today the graduation exam with the grades specified hereafter. Emam 104, 104. Kazemi Pur 110 cum laude, 110 lode. Najari 106, 106. Sabatucci 110, 110. Salustri 110 cum laude, 110 lode. Sensolini Arra 110, 110. On behalf of the Rector of Sapienza University of Rome, I confer to them the master degree in control engineering. Congratulations. And one of our students accessed the student honor program is Amir Hossein Kazemipur. So this is just a recognition that the completion of congratulations. Okay. So thank you for doing your work with Sapienza and with our department and in control engineering. You are responsible for a good future of this area, and I'm sure that you will contribute in any sense in research, in your professional life, with your competence. And this is also a very good point for us as professor. I just want to add a personal story here, namely that today, 40 years ago, I graduated in engineering. So I wish you all the best to do better than I did, and it's good enough. So congratulations e complimenti a tutti quanti, anche i vostri.